Okay, so today we're going to go over fission and fusion. So fission is the splitting of larger nuclei into two or more smaller nuclei, so they're going to break apart. So the most common everyday thing that's used in this is it occurs in nuclear power plants, and all it's doing there is heating water. It's turning it into steam, and that steam's going to run the turbines for it with it. So it does have to have a radioactive source that's unstable and is going to want to split here. So we're going to go ahead and add some symbols on here. I'm actually going to turn this the other way because it's kind of messing around this one I imported. Nah, this is about the same either way. All right, so sorry, this is moving this around a little bit. Ignore this on here. So the first thing I want you to do is identify the symbols for each of these. So you see bottom numbers of 92, 0, 56, and 36, and then also the neutrons as well. Okay, so go ahead and look those up and fill those in. Okay, so you should have looked up element 92, and that is uranium, so you put a U here. The next one is 1 over 0 on here, so that means the mass is affected, but it doesn't have a proton, so therefore that must be a neutron. So this here should have an N. So I started off with uranium-235. I added a neutron, and that's going to help split it. So when I split it here, my first one is 142 over 56, so you should have looked up what element 56 is, and that's barium. Again, use the bottom numbers. This is barium-142. Your next one is 91 over 36. 36 is Kr. And we also see here that you get 3 more neutrons, so 3 1 over 0 N. So as you're adding the total up on here, we have to make sure that these add up. So 235 and 1 is 236. 142 and 91 is 240 or 233 on here. But then you have 3 neutrons, so they each give 1. On bottom, 92 and 0 adds up to 56 and 36, and the 0. So why we like this, it is a chain reaction, which means as long as there's enough material, we're going to call that the critical mass, the extra neutrons produced can keep the reaction going on there. So every time you do this, you get more and more neutrons, which can split more and more of the uranium or whatever fuel you're doing here. The other thing is that this is easily done. It's been going for years. It's efficient, and we can be using it in power plants all over the world. The disadvantage, though, is it produces lots of waste. So we have something in there called control rods that hold the fuel with it. Even things like paper towels and different things that could have been exposed to things have to be treated with it. So they have to decide what they're going to use for the waste. The other thing is that some people are afraid of nuclear power plants. They don't necessarily want them built by them. They're not in support of them with it. Not everyone is in that case, but there is definitely a portion of the country that does not like to have these in there. So just public perception. So the opposite of this is fusion, and that's taking smaller nuclei and combining them to make a larger one. So you can think of this like fusing glass. They melt glass down and put it together to make a bigger piece from there. So the most common place this happens is in the sun. So let's think about what symbols these would have on here. So element 1 is hydrogen. So that's a form of hydrogen, is hydrogen 2, or known as deuterium. We have another isotope of hydrogen, hydrogen 3, or that's known as tritium. 4 over 2, you're making helium. And then you have another neutron here, and again, sorry, this is kind of changed my PowerPoint around a little bit. And then it releases a lot of energy. So lots of hydrogen that's in the sun can be used to make helium, put things together, and give off energy from it, but of course it has some problems too. And the problem is on here with it. So the advantage on this is it produces a ton of clean energy. Doesn't have all that waste to it. The disadvantage of it is it hasn't been done yet for an energy benefit. And the reason why is it requires such high temperatures. So just like you're producing something, you're making something, and maybe people would pay $50 for it. You add up your materials for it, and it costs you $60. Well, yes, you can make it. Yes, people will buy it, but unfortunately, you'd be losing money. So that's the same problem that we have with fission and fusion right now. Is the high temperatures to push those things together, because again, things have charge that they want to repel each other if they have the same charge with it. You've got to get high temperatures to move them fast enough so that they can fuse from it. So they are making progress in this. You've probably seen some movies at some point that had something about cold fusion. With it trying to do it at a lower temperature, but we're not there yet, and who knows, maybe in your lifetime it will happen. All right, go ahead and take the Fission and Fusion Canvas quiz. You can retake it if you're not happy with your score, but since most of the answers are fission or fusion, it's not going to tell you which ones you missed. It will keep your highest score, however.